Hello, I welcome you all to this another interesting screencast, and the problem reads: the boom DF of the jib crane and the column DE have a uniform weight of 50 pounds per feet. If the hoist and the load weigh 300 pounds, determine the normal force, shear force, and moment in the crane at sections passing through points A, B, and C. Okay. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have a crane and a column, and both have the uniform weight of 50 pounds per feet, and there is a load that weighs 300 pounds. And we are being asked to determine the normal shear and moments in the cranes at sections passing through points A, B, and C. So what I've done below here is I have redrawn this particular crane and column DE using the line that goes through the neutral axis. Okay, the neutral axis is an axis that has zero longitudinal stresses and strains. Okay, and normally this is what we normally use for modeling structures like this one. Okay, so I redrew it here. So we have the uniform weight on top. Okay, we have the uniform weight like you've been told in the problem of 50 pounds per feet. Okay, on the crane beam, and as well as we have 50 pounds per feet on the column DE. Okay, and we also have a load of 300 pounds that this crane is supporting. All right, and it is fixed at E. That's a fixed support. Right, so having drawn this particular structure in this manner, we now need to just add the support reactions, which is a free body diagram. So this distributed force, which is the uniform weight of the crane, will be acting at the midspan, right? All through the centroid. So at the midspan, all right. And the distance will be just half the length of this rectangular uniformly distributed load, which is the uniform weight. So this length is 2 plus 8, 10 plus 3, 13. Half of 13 is 6.5. Okay, that's 6.5. And this weight is, the equivalent weight is just the area under this load diagram, which is just equal to the intensity itself of the load times the length, which is 13. And this gives us that 50 by 13 is equal to 650 pounds. And also this distributed force, which is acting on the column, okay, is axial distributed force. This equivalent force will also be acting at the centroid, which will be the midspan of the column. So let's say it will be acting somewhere there. Okay, so let's say that is the load there. That is the equivalent force, that's why it's acting. And it will also be equal to the intensity 50 times the length of the column, which is 12. Okay, and this is equal to 600, right? This is equal to 600 pounds. Great. So at E, which is the fixed support, we are going to have all the reaction forces, the vertical, the horizontal, of course, AX, as well as moment. Okay, which is just this is all supposed to be EY. Okay, this is EY. This one there is EX, and the moment is ME. Great. So those are the reaction forces at the fixed support E. So we are going to apply the equations of equilibrium as usual. And the length where this, I didn't indicate where this this equivalent force on the column is acting is at half the length of the column. Let me indicate it. Half the length of the column. And this length is 6 feet, half of 12, 6 feet. Okay, that's where it's acting. Right, so we've done everything else. Let's now apply the equations of equilibrium quickly and then find out the values of EY, EX, and ME. So we have summation of moments about point E equal to 0 anti-clockwise. And then I also forgot to mention to say, not only are we going to find the internal forces at A, B, and C, but we are also going to draw the shear force and the bending moment diagram for member DF, which is the crane, as well as the column DE. Okay, right, let's go ahead now. Summation of moments about point E equal to 0, anti-clockwise being our reference. What do we have? We have a minus moment due to 300 by the lever arm. What's the lever arm? About E, that's 13. And then we have another negative moment, and the lever arm is 6.5. What else? This is about it. Okay, plus ME equal to 0. Therefore, our ME is going to give us, let's grab our calculators, minus 300 times 13 minus 650 times 6.5. Okay, so we have ME is equal to 81.25 pounds feet. Alright, and then we have summation of forces in the Y equal to 0. What do we have? We have minus 600 minus 650 minus 300 plus EY equal to 0. Therefore, our EY will give us, what do we have? Minus 600 minus 650 minus 300. Alright, so this gives us a 1550 pounds feet. Alright, what else? Summation of forces in the X equal to 0. Alright, in the X we don't have any force, and therefore EX Ex will just be equal to 0, right? Ex will just be equal to 0 pounds. All right, so we found the reaction forces. What we need to do now is to start doing the section. Okay, so we'll do our section here at A, which is this point. I've done down also there. So we have the left hand section and the right. Now this one is right. We have the right hand side section, right hand section, and the left hand section. We go with the simplest one. So we are going to go with the simplest one. So we have done a section, we'll call it section C. So we'll go with the simplest one, which is the right hand section. So I'll pick that one, and then we are going to replace it with the loads. So we have a distributed force on that section. This point is F and this point is A. So we have a distributed force like this of 50 pounds per feet, okay, per feet. And we do have an equivalent force there. The length of this part is 3. The length of this is just a 3 feet. Therefore, the equivalent force itself is just going to be the area under the load diagram, which is the intensity 50 times 3. This therefore gives us 150 pounds. And it's going to be acting at half the length of this section, which is just 1.5. Okay, so here we expect a shear force VA, right? VA, and a moment MA, and a normal force NA, right? So let's apply the equations of equilibrium. So we say summation of moments about point A equal to 0, and clockwise being our reference. What do we have? I forgot also to indicate here, we're going to have this load, which is a 300. Okay, so we are going to have 300 by 3. Okay, this is anti-clockwise, and then plus 150 by 1.5, and then plus MA equal to 0. And therefore our MA will give us, so we have 300 by 3 plus 150 by 1.5. So this gives us a minus 1125 pounds feet. Okay, so let's move on to the next space. So let's find the shear force. So summation of forces in the y equal to 0, going up being our reference. So we have VA minus 150 minus 300 equal to 0, and therefore our VA is just going to be equal to 450 pounds. And then we have summation of forces in the x direction. Do we have anything in that direction? Therefore, our NA is just going to be equal to 0 pounds. So we are done with our first section. So make another section at B, this point here, which is here, right? Great. So we have the right hand section and the left hand section. Which one do we go for? Of course, we are going to go with the simplest one. I will pick the right hand sides. Okay, so let's draw that quickly and start doing the work. So this one is section B. Okay, so let's pick the one that is simpler, and we already chose it, so we are saying we'll pick the right hand side. All right, we'll pick the right hand side. What happened? Okay, up to there, like so. Great. So this point here is F, and this one here is B, and we have A somewhere there. We have a distributed force here. We do have a distributed force, like so, and this intensity is 50 pounds per feet. The length of this from F to B, this is 3 plus 8, which is 11. Okay, so we have here VB. We have the moment. I've run out of space. Let me reduce my section a little bit, maybe up to there, like so. Okay, so this is our B. The section comes up to here. All right, so we have VB, we have MB, we have NB. Okay, and then we are going to have an equivalent force there, which is just going to be equal to the intensity 50 by the length 11, and this gives us a 550 pounds, right? And is acting at the length half of 11, which is just 5.5. Great. Then let's apply the equations of equilibrium. So we have summation of moments about point B equal to 0, and clockwise being our reference. Of course, here we have another load, which is 300 pounds. All right, so there we go. So we have 300 times 11, okay, plus 550 times 5.5, and then we have plus MB equal to 0. Therefore, our MB will be equal to, let's find what this is, 300 by 11 plus 550 by 5.5. So this gives us a negative 63.25 pounds feet. 300 by 11 plus 550 by 5.5, 63.25. Then we have summation of forces in the y equal to 0 going up in our reference. And we have, of course, we have VB minus 550 minus 300 equal to 0. Therefore, our VB is going to be equal to 550 and 300. This gives us 850 pounds. And then summation of forces in the x direction, of course, equal to 0, we expect NB to just be equal to 0. Okay, to just be equal to 0 pounds. Great. Right, let's close this so that we work on the other section. So let's also do another section at C at this point here, which is this point here. Okay, so let's draw this section. So we have the bottom, section, and the top section. All right, so let's draw it. We're going to have something like this. So at the very bottom there, we have the reaction forces. EY, we said, I didn't indicate this, we said ME was equal to 8125, EX was equal to 0, okay, and EY was equal to, where is EY? EY was equal to 1550. Okay, right, so here we have a 1550, okay, and then we have a moment of 8125, and then we have a distributed axial force which is constant. Okay, this point is C. Of course, we are starting from this point going up like this. Therefore, here we expect a shear force of BC and a moment like so of MC and NC like that. Okay, so, and this intensity here for this is 15 pounds per feet, and we are going to have, okay, so let's go ahead and work out this problem. And this intensity for this axial distributed force will be acting at this centroid, which is half the length of this beam. How long is this part? This part is, let me put this length aside. This, where the distributed force will be acting, this part is E there. It will be half the length of C is where at 7, right? So at 3.5. And the whole length of this beam is 7. This is a 7 feet. Okay. Then let's start now applying the equations of equilibrium. Summation of moments about point C equal to 0, and clockwise being our reference. What do we have? We have 8125 plus MC equal to 0. Therefore, MC is just going to be equal to minus 8125 pounds feet. Then we have summation of forces in the y direction equal to 0. What do we have? We have 1550. And then we have this load. We said this equivalent force this equivalent force is equal to 50 times the length, which is 7. Okay, so this gives us a 350. Okay, so, and it's acting at the centroid, which is at 3.5 meters from E. So we have 1550 minus 350 and then plus NC equal to 0. And therefore NC is going to be equal to, we have 1550 minus 350. This gives us a minus 1200, right? A minus 1200. Okay. Yeah, minus 1200. Great. And then finally, we have summation of forces in the x direction equal to 0. Okay. And in this direction, VC, which is the shear, is just going to be equal to 0 pounds. All right. So we've found everything for the sections. We have MA, okay, which is this negative moment. We have VA, which is a positive shear. We have NA, which is 0. And then for section B, we have a negative moment. Okay. For the shear, we have a positive shear of 850. And NB, we have 0. And then at section C, we have moment, a negative moment, 8125. We have a normal force, a negative value, and then shear is equal to 0. Great. Right. We had also said we want to draw the shear force bending moment diagram, and I also include the axial force diagram. So we'll need to make a section here for this crane beam, and also a section here for this column DE. So I've done the sections already on the next page, so that quickly we apply the equations of equilibrium, which I will not show. I'll just do them quickly and then later on start doing the drawing. All right. So here are the two sections that we've separated. Of course, like we said, we need to make a section here, okay, and there. All right. And we are going to be moving from E to D along the column as we begin to plot. You've seen here, we are moving in this direction. And then from B to F, we are going to be moving in this direction like that. Okay. I've indicated already the plus and minus for all of them. Okay. As well as this being the axial force diagram, shear force diagram, and bending moment diagram. So let's do this quickly. Time is not on our side. So when these are sections, we are going to have internal forces D and T. D for the crane beam, and also at D there for the column. All right. So when you apply the equations of equilibrium here, okay, you apply the equations of equilibrium here, you are going to expect a normal force, okay, a normal force of magnitude. This one is going to be equal to when you apply summation of forces in the y. If you did that, you applied summation of forces in the y, okay, summation of forces in the y direction, okay, going up being positive. So you have 1, you have 1550 minus the axial distributed force 50 by 12. Okay, so if you worked out that, okay, let's say this value is n also. Okay, so that I do it normally, then minus n equal to 0, therefore your n will be equal to 1550 minus 50 by 12. Okay, so this gives you a 950. So therefore this value is 950. Okay, this value is 950. And then we are going to also expect a moment here, all right, here. Okay, this moment also, if you are to apply summation of forces, let's call it m. So summation of forces about point D equal to 0 and clockwise being our reference, you have this one is clockwise, so we have minus m plus 8125 equal to 0, therefore m is going to be equal to 8125. So this m is also equal to 8125. So this one is 8125. Okay, we don't have any shear there in the column. Okay, so I'll not even work on it. And the same applies to this. We expect also here a shear. Here we expect a shear force. Let's call it V. So if you are to apply summation of forces in the Y there, okay, you have V, you have an equivalent force there that we had calculated, which is a 50 by 13, which is equal to, I think, 650, right? Okay, 50 by 13 equal to 658. So if you are to sum up those forces, so you have V minus 650 minus 300 equal to 0, therefore V is going to be equal to 950. So this V is equal to 950. So let me write it there. This is equal to 950. Okay. All right, and then you expect also moment here, which will have the same magnitude as that one there. Okay, because where we cut a section that is continuous, you expect the same internal forces. The only thing that they will have is opposite direction, right? Okay, so that moment there, let's call it M. So if you are to apply more summation of moments for the crane beam, okay, for the beam, and clockwise about D, then you expect M, which is unclockwise, then you expect a minus 650 by half of 13, which is 6.5, and then a minus 300 by 13 equal to 0. Then M is going to be equal to 650 by 6.5 and 300 by 13. So it's 8125, the same moment, all right? The same moment, 8125. Okay, so let's put it there. 8125. Great. So these are the results that we expect, and I expected these results. So now once we've done that, then quickly let's start drawing the equations that we're going to use for the axial force. For the axial force, we are saying the change of axial force with respect to, in our case, with respect to y, okay, along that y, okay, is just equal to, we are going to be plotting it along the y, is equal to q, okay, and therefore the axial force itself will just be equal to integral under the loading diagram dy. And then for moments, okay, let me just use one symbology so that we don't get confused. So the change of axial force, the change of axial force with respect to x can be any axis. In this case, it is y. All right, this is going to be equal to q, and therefore axial force itself is just the area under the distributed loading diagram, which is the axial force in our case. Okay, this axial force is distributed along the column, and then we have the change of shear with respect to x is also equal to the distributed load, and shear itself is just the area under the loading diagram perpendicular to the beam. All right, dx. And then we have the rate of change of moment with respect to x is equal to shear, and moment itself is just equal to the area under the shear loading diagram. So these are the equations that we're going to use, right? So now at E we have an initial value of minus let's say minus 1550 pounds. All right, so we said from E to D, our Q there is equal to, is constant, okay, is constant, and therefore our dA dx, which is the slope of our axial force diagram, will also be constant. All right, and this magnitude, like we say, just the area under the axial force, axial distributed load, which is q dx. Okay, instead of x we are along the y, but you don't have to worry about that. And then the load, we can calculate it since it's uniform, so it's just a 50. Okay, it's a 50 times the 50 times the length, which is 12. Okay, it's 12, right? So 50 times 12 is 600. Okay, so 600. So when you look at the sign, 1550 is going up, and that's the sign we've chosen as our negative. So anything that will be going in the opposite direction, we need to subtract it. So from E to D, from E, because our initial value here is 1550, and then the other value that we just found in between E and D is 600, so we need to subtract it from 1550 so that we see where we're going to, the final value of our destination. Okay, so 1550 plus 600, this should give us minus 1550 minus 1550 plus 600, so this gives us a minus 950. So we'll move from here. Okay, like we said, it will have a constant slope, okay, which is linear. Okay, because the load is constant, therefore axial force, we expect it to be a polynomial of degree 1. So let's say that is our 900 950 rather. Okay, let me start again. Okay, let's say somewhere there, that is our 950. Let me write it down. That is our 950 pounds. All right, so when we reach there at D, we do have another force that is in the opposite direction. Therefore, we have a minus 950 plus 950 equal to 0. And hence the what? The closure. Yes, closure. So this has to close. All right. So this is negative. This is negative. So let's go to the shear diagram. Let's wrap this. We don't have any shear from E to D, right? We don't have any shear loading from E to D. So this is just going to be along the 0 axis like so. All right. Then from D to F, we do have something. Let's look at the initial values that we have. Initial value at D, we do have a value of 950. Okay, going up, so we have a positive value like so. Let's say 950 is somewhere up to there. All right, so let's indicate that value. Let's say this is our 950 pounds, right? Then from D to F, our Q is equal to is negative and constant, and therefore our dv dx, slope of our shear diagram, is also going to be negative and constant. And this magnitude is just q dx, which is just equal to a minus 50 times 13. This gives us minus 50 by 13 it gives us minus 650, right? It gives us a minus 650, does it? This is minus 650. So now the two are going to interact. We have 950 minus 650. What does this give us? 950 minus 650. This gives us a 300. So we expect a reduction here from there to positive 300 up to somewhere there. Let's say up to somewhere there. All right. So that is our 300. That is our 300 pounds. All right. The moment we reach there, the two are going to interact. At F there, we have another value of minus 300. So we have a positive 300 minus 300, which gives us what? 0. This brings about what? Closure. So this has to close here. It will close here like this. Great. So this shear that we have here is positive shear. Okay, great. So we've drawn the shear diagram. For this. Let's draw the moment diagram. So for the moment diagram, let's look at the boundary condition at E. What do we have? At E, we have a reaction moment of 8125. Remember, if we are to cut a section just on top of E, we are going to have an internal moment that is going to have opposite direction to 8125. Okay, so every time you see an applied moment or reaction moment, like in this case, just get the opposite, right? When you're drawing this diagram, get the opposite direction of that moment, right? So here we have 8125, which is positive. Therefore, when we come to draw, we are going to consider a negative. Okay, so we have this boundary value of a negative. From there, let's say this is our negative value. This is our negative value of magnitude 8125 pounds feet. All right. So once we have that, let's look at what we have from E to D. Do we have anything? What is our V? Our V is equal to 0, and therefore our dm dx is just going to be equal to 0. So this is just going to be a straight line. Great. Just a straight line like so. Maybe this is too wide. Maybe reduce it just a little bit. This is too wide. Maybe up to somewhere there. Great. Okay. So let's draw it. It's just going to be a straight line to there. And then when we reach there, we have another moment there. I mean, this moment, this one here. Where is it? We have this moment here. Again, when you look at the direction, just get the opposite. This direction is clockwise, therefore the opposite will be what? Will be anti-clockwise. So this one is positive. What is our value there? Our value here is a minus 8125, then plus opposite of clockwise is positive, right? So plus 8125 equal to 0. So this is the one that is going to close our diagram. It will close our diagram at this point. Okay, so closure, there we go, like so. Okay, right. So this value is 8125 pounds feet. Great. Okay, and this is negative, right? So then let's look at what we have from D to F. From D to F, what are the boundary conditions? From D to F, we have counterclockwise of 8125. What did we say? So this one, what we have here is a positive one, so we have to go to what? To a negative one, right? That is our boundary. All right. So let me use blue. So we'll move from there. It will have a magnitude of 8125. So this one is 81. This is 8125 pounds feet. All right. So from there onwards, what do we have? We have shear, which is equal to this diagram. See this diagram? We have shear, which is positive and decreasing, right? It's decreasing in slope. and therefore we expect the slope of our moment also to be positive and decreasing, right? And what is magnitude? Magnitude is just the area under the shear diagram, which in our case is just a trapezoid. So let's find the area of the trapezoid. 950 plus 300 plus times half times the length or the height, which is a 13, right? So what does this give us? So 950 plus 300, okay, times half times 13. So this gives us 81.25 positive. All right. So then the two will interact so that we find the final destination. We have a minus 81.25, then plus what we found 81.25. This is going to be 0. Okay. This is just going to be a 0. So we need to look at the function that governs our shear. The function that governs our shear is a polynomial of degree 1. Therefore, you expect the function that will govern the moment from D to F to be a polynomial of degree 2 or a quadratic, right? And when we look at the slope is positive and it is decreasing, right? So you know how the slope is going to be positive, but what? Decreasing. So you expect a behavior like this up to there. Okay, let me draw it properly. Okay, something like that. Great. So, and that particular is also negative. This is negative. All right. Okay. So this is really about it. This is really about it. We have done everything that we were expected to do. We found the internal forces at A, B, and C, and we also decided to draw the axial force diagram, the shear force diagram, and the bending moment diagram. Right. I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.